So last class, we talked about Markov chain Monte Carlo and the application of calculating the internal energy of a gas based on the temperature of the gas and based on this random walk through the microstates of the gas. In this class, we're also doing a Markov chain Monte Carlo. We're going to think about the magnetization of a solid ferromagnet, and we're going to solve it by taking a random walk through the microstates of the ferromagnet. So I got two or three slides that are just introductory remarks on magnetism and matter to give us some foundation for the calculation. Then I've got some remarks on the Markov chain Monte Carlo method and the Markov chain Monte Carlo method specific to the magnetization of a ferromagnet. And then I'll move to the code. So that's basically the plan. So just as a very basic starting point, obviously electrons, essential components of matter, they carry both charge and magnetism. So they have electric charge, they have a magnetic moment. Their magnetic moments, due to the quantum nature of electrons, the quantum nature of their magnetism is that it can be spin up, it can be magnetization aligned, or it can be spin down, magnetization anti-aligned with some chosen magnetization axis. So we've got aligned or anti-aligned magnetic moments from electrons, spin up, spin down electrons. There's two categories of magnetic materials that I wanted to mention. One category is diamagnetic materials. The other characteristic material is paramagnetic materials. So in diamagnetic materials, all the electrons are paired up together. So obviously it has an even number of electrons. And those materials have the property that they are weakly repelled by magnets. And I'm not going to be talking about those. The other type of material, paramagnetic materials, are materials that don't have every electron paired up. There's lone electrons, for example, and those are weakly attracted by magnets. And I am going to be talking about those materials. So that's just a very broad background on magnetism and matter, these two categories, diamagnetic materials, paramagnetic materials. That is a practical matter, either experience sort of mild repulsion from magnetic fields or mild attraction to magnets. Paramagnetism and ferromagnetism. So paramagnetism and ferromagnetism are related. In fact, materials that typically, depending on the temperature, exhibit either para or ferromagnetism. So let's explain that a little bit. Paramagnetic materials then are assemblies of atoms and molecules where those atoms and molecules, or the electrons accompanying those atoms and molecules, have dipole moments due to the electron's magnetism. So we're going to be thinking of them as kind of collections of microscopic dipole moments. So when we're thinking of paramagnetic material, let's just imagine the inside is just this huge collection microscopic dipole moments. In what we call an ideal paramagnetic material, those dipole moments, microscopic dipole moments of the material, would interact with the surrounding magnetic field, an external magnetic field, but they don't interact with each other. Their interactions between each other is too weak. In a real paramagnetic material, then those dipole moments would interact with external magnetic fields, be influenced by external magnetic fields, but they would also interact with each other. And that's what we're going to focus on in today's class. In particular, in paramagnetic materials, the atoms or molecules, the little dipole moments, tend to interact with their nearest neighbors. And their interaction with their nearest neighbors might lead to a preference for them to align up with each other. That could be one case, or it might lead for a preference for them to anti-align with each other. So that would be another case. These interactions between the neighboring dipole moments, whether they are tendencies to align or anti-align, lead to ferromagnetic materials, which are where the dipole moments prefer to line up. So iron is a classic example of a ferromagnetic material. The individual dipole moments of the ions or the electrons, the lone electrons associated with the ions, want to line up with one another, and that creates ions magnetization. There is another case called antiferromagnetic materials. That's where the individual dipole moments want to anti-align with one another, line up opposite one another. And chromium is an example of a material where the dipole moments want to line up opposite to one another, and that's called an antiferromagnetic. It's actually complicated whether a material is a ferromagnetic rather than an antiferromagnetic. It really depends on details of the overlap of the wave functions of the electrons that are producing the dipole moments with one another. So it comes down to the detailed structure, detailed orbits, wave function overlaps of the electrons with the neighboring electrons as to whether material is ferromagnetic, like iron, where the dipole moments want to line up, or antiferromagnetic, like chromium, where the dipole moments want to be in opposite directions to one another. Okay, so some properties of ferromagnetic materials. I've listed some properties of ferromagnetic materials on this overhead here. So in ferromagnetic materials, what can happen is a long range by meaning not just the nearest neighbors, but over many extended neighbors of the system, there is a long range ordering of the dipole. So they tend to line up through the material or some region of the material. This causes a non-zero macroscopic magnetization of the material. That's what a magnet is. It causes a non-zero magnetic energy of the material. That also what a magnet is. It tends to be that if you raise the temperature of the material, you'll raise the thermal fluctuations of the material, you'll raise the kind of random fluctuations of the material, and the amount of magnetization or the amount of alignment will shrink, will decrease. If you lower the temperature of the material, that is, you'd be lowering the thermal fluctuations in the material, lowering the random fluctuations in the material, you tend to have the magnetization grow or increase. So those are two features of ferromagnetic materials. And between those two regions, right, where the dipole moments of the ferromagnetic material tend to line up, and where the dipole moments of the ferromagnetic material tend to be randomly directed, is a critical temperature. And this is the critical temperature which an alignment in the material would appear. So below that critical temperature, the the atoms or the dipole moments are lined up with one another. Above that critical temperature, the atoms and molecules, the dipole moments in the material would not have the alignment with one another. They would be randomly aligned. So there's really a phase change in materials, in ferromagnetic materials, between a phase in which the when the ferromagnetic material is above the Curie temperature, above this critical temperature where the dipole moments are randomly aligned, and below that critical temperature where the dipole moments are aligned with one another. So above the critical temperature, you get a macroscopic magnetization in the material. Below the critical temperature, you get a magnetization in material. So that's this point here. So it's the reason why you can prepare magnets or destroy magnets by heating and cooling. You can if you heat up a magnet, you can destroy its magnetization. If you cool down a magnetic field, you can create its magnetization. In detail, the magnetization of a material is a magnetization in domains of the material or regions of the material. So if you were to peer into a magnet, you would see these different regions, these different domains. The regions or domains are kind of, they're macroscopically small, but they're microscopically large. So macroscopically small would be that they're much smaller than the size of, your everyday magnet. Microscopically large means that they're large collections of atomic and molecular electron dipole moments. So they're made of many atoms of molecules. So those are the domains. Within a domain or region, of a ferromagnet, the atoms or molecule dipole moments tend to line up with one another. And then between neighboring domains or regions, those domains or regions tend to anti-align with one another. Okay. So this slide, which I was missing on the slide, is a introduction to a model of ferromagnetics. It's going to be our model of the ferromagnetics for our calculation of ferromagnetics. It's what's called an Ising model. So the Ising model models the short-range interactions between the nearest neighbors of magnetic dipoles in the magnetic material. So it's going to model that interaction. And in the Ising model, typically you ignore interactions between not nearest neighbors, more distant neighbors of the dipole moments. So we're just going to model the nearest neighbor dipole moment interactions, and we're going to ignore the neighbors that are further away in their dipole interactions. So that's the first bullet upstairs here. The way we model the interactions is that for the nearest neighbors, there's a characteristic magnetic energy associated with their interaction that is either positive or negative, depending on whether the two dipole moments that we're interested in their interaction with they're either aligned with one another or oppositely aligned with one another. So in a ferromagnetic situation, if the two dipoles are lined up with one another, that's the preferred situation, and the energy is lower. And in a ferromagnet, if the two dipoles are lined opposite one another, then that energy configuration is higher. So that there's an energy difference between being aligned and being anti-aligned in a ferromagnetic, and also in an anti-ferromagnetic. There's an energy difference between being aligned and anti-aligned. It's just in the ferromagnetic, the dipoles want to align opposite one another and prefer not to align in the same direction as one another. So that's the basic idea. Now let's imagine that we had a magnetic material that was just a one-dimensional magnetic material. It was just a straight line of little dipole moments in a row. So the magnetization of that material, if you think of each dipole moment just interacting with its neighbor, and just interacting with its neighbor where the energy is, if they're lined up, is minus epsilon, and they're anti-aligned is minus epsilon. So just a simple interaction with that's an analytically solvable problem. One-dimensional material, each dipole just interacts with its nearest neighbor, so the one to the left and the one to the right. It's a negative epsilon interaction energy if they're lined up. It's a positive epsilon interaction energy if they're anti-aligned with one another. That model is analytically solvable, and the equation for the wrote it down here. The equation for the magnetic energy of that one-dimensional system is this little equation here. It's minus n epsilon. So epsilon's the energy associated with one pair of interactions. N is the number of atoms or dipoles in the system, times this hyperbolic tangent function. And the argument of the hyperbolic tangent function is a ratio. It's a ratio of two energies. It's a ratio of the magnetic interaction energy between a pair of dipoles, that's the epsilon in the numerator, and the characteristic thermal energy of the system, that's the KT in the denominator. So a hyperbolic tangent function is a interesting function. If in the limit that the argument goes to zero, so one limit is where this argument goes to zero. So that's the limit where the magnetic energy will be much smaller than KT. That leads to the argument here approaching zero. Then the hyperbolic tangent is zero also. And in that case, you would have no magnetic energy. And in that's the case where the magnetic interaction energy was much, much smaller than the thermal energy KT. So that's a case where the magnetic energy that wants to line things up loses out. The thermal energy, which wants to randomize things, wins. And so you have a random arrangement of dipoles in this one-dimensional material. And so you have, because of random arrangement of dipoles, there's many alphas down. Then you have no net magnetization, you have no net magnetic energy. So that's one limit when the argument here is small, which means that the magnetic energy is smaller than thermal energy. The other limit of that equation, right, is where the argument in the hyperbolic tangent is much, much larger than one. So, the limit is infinity. That's where the magnetic energy is much greater than the thermal energy. So hyperbolic tangent has the property that if this argument is large, then the hyperbolic tangent goes to 1. So this approach is 1 when the magnetic energy is much greater than the thermal energy. And as you can imagine, if the magnetic energy of the interaction is much greater than the thermal energy, and the little dipoles want to line up with one another, they'll all line up with one another. That gives a hyperbolic tangent that's 1, and it gives a magnetization for the material, which is just, it gives a magnetic energy for the material, which is just minus NP. So it's minus because it's wanting to do that. It's going to find this lower energy magnetic state by lining all the dipoles up. It's N times epsilon, because epsilon is the interaction energy of a pair of dipoles, and then we've got an arrangement of n dipoles. So that's the total magnetic energy. So you get this simple result, which I think you can picture or imagine. If you had a two-dimensional material, so this is a one-dimensional material that you can solve analytically. If you had a two-dimensional material, so like a sheet of dipoles, an array of two-dimensional array of dipoles. That was a mathematical problem that existed for 20 years to analyze. Suddenly, big mathematical problem existed for 20 years to solve that analytically and write down the magnetic energy or the magnetization. But there is an analytical solution to that. But still, nowadays, there's no solution to a three-dimensional array of magnetic dipoles in this simple model of nearest neighbor interactions and writing down an analytical expression for the magnetization of a three-dimensional array of dipoles. The point of the statements about the 2 dimensions and the 3 dimensions is that whilst analytically the problem of one-dimensional array of magnetic dipoles is relatively easy to solve and write down a simple expression for, whereas the problem for 2 and 3 dimensions is either very difficult or impossible to write down an expression for. If we solve the problem by Markov chain Monte Carlo on a computer numerically, then 1, 2, 3 dimensions is just as easy as each other, basically. So that's the route that we're going to go. As I say, this equation up here for 1 dimensions exhibits these features that I mentioned of ferromagnets. At low temperatures, where the magnetic energy is greater than the thermal energy, the dipoles will line up with one another and you got magnetization. At high temperatures, where the thermal energy in the denominator here is greater than the magnetic energy in the numerator, then the dipoles are arranged randomly and you got no magnetization. And between those extremes of alignment and disorder, there's this critical temperature where the ferromagnetic would undergo this phase transition from an ordered to a disordered array of dipoles. And so that's a key feature of ferromagnetics, and it's embedded in this equation or a one-dimensional ferromagnet. And we're going to try and reproduce that in a Markov chain Monte Carlo calculation. So we'll focus in my code on a two-dimensional array of dipoles. We'll just focus on that because it's just quicker to calculate the magnetization of a two-dimensional array than a three-dimensional array. But the code that we're writing for the two-dimensional array could easily be extended through a three-dimensional array and just have to wait longer to study the magnetization. The point is that what Markov chain Monte Carlo allows you to do is to calculate the magnetization or calculate the magnetic energy. Instead of walking through every microstate in a macrostate to calculate the magnetization or calculate the magnetic energy, we can just take a random walk through the microstates of macrostates to sample and figure out the magnetization and the magnetic energy. Okay, so this is going to be a procedure again. This slide is the slide from the last class. So this was the procedure for calculating the internal energy of a gas at some temperature. And this is going to be a procedure for calculating the magnetization or magnetization energy of a ferromagnet at some temperature. So it's exactly the same procedure, except now our physical quantity, for example, would be the magnetization of the ferromagnet or the associated magnetic energy of the ferromagnet. We start in the same way again as we did in the last class, right? Last class, we just picked a starting point, a starting microstate. In the last class, I think we pushed everything was in the ground state, and then we followed this random walk away from that state into more likely, more probable states. So we'll pick a starting point in this class. In this class, I'm going to do something that you would more likely do if you're a kind of a professional Markov chain Monte Carlo calculator, you might start, a random distribution of your states rather than with everything in the ground state. So I'll start out our Markov chain Monte Carlo calculation by just randomly distributing the dipoles in up or down orientations. So we'll start out with a state, and then we'll do exactly the same procedure in steps 2 and 3 as we did in the last class. In the last class, we picked an atom, and once we picked at random an atom from the collection of atoms, we would try and raise or lower its energy, and we would accept or decline that raising or lowering of its energy based on a Boltzmann factor. We're going to do the same here. So I'm going to pick randomly a dipole moment, magnetic dipole moment in that collection of dipole moments. So just pick one of them, and I'll then try and flip its orientation. So if it was up, I'll try and flip it down. If it's down, I'll try and flip it up. I'll accept or decline that flip from up to down or down to up, based on, again, based on Boltzmann equation. So in that way, we're following exactly the same procedures we did for the internal energy of the gas. Picking an atom, picking a molecule, picking a dipole moment, thinking about changing its state, and accepting or declining the changing of state based on the Boltzmann factor. And then we'll just repeat this many, many times, thousands of times, tens of thousands of times, 100,000 times, till we can equilibrate or thermalize or burn in the system. That is, burn it, thermalize it into a common microstate. So that's the plan. A few more details on the implementation for the ferromagnetic. So these are details that are different from the implementation for the internal energy of the gas. So I'm going to work with a 2D model. So that's the first thing upstairs here. I'm going to just think about the interaction energy between nearest neighbors in this 2D model. So imagine, as an example, you can imagine a chessboard, right? And each square on the chessboard is a magnetic dipole. And supposing I pick one of the squares on the chessboard, I'm going to consider that as having 4 nearest neighbors. So no, I'm not going to include the diagonals. I'm just going to include the 4 absolute nearest neighbors to each dipole. And that's the interaction that I'm going to consider. So we've got 4 nearest neighbors. This is going to be my expression for their interaction energy. And actually, this is the expression for the total interaction energy with the 4 nearest neighbors. S is just an integer to indicate whether the spin is, or the dipole moment is up or down. The products of Xi and Sj are just the products of the spin up or spin down, the +1 or the -1, for the dipole that we're considering and one of its nearest neighbors. So that product, Si times Sj, where Si is either +1 or -1, and Sj is either +1 or -1, depending on whether the atoms are aligned or anti-aligned to the magnetization axis. That product is going to be either +1 or -1. It's going to be +1 if the 2 atoms are aligned with one another. 2 magnetic dipoles are aligned with one another. It's going to be -1 if they're opposite to one another. So that's going to, this product here is going to give us a sign. This J is the notation here is the strength of the magnetic interaction. So it's just the size of the magnetic interaction. It's going to be in units of kT, so it's going to be in units that are convenient for the calculation when we calculate the Boltzmann probability. So this is an interaction energy. And the minus sign out front, it just will mean that if the two atoms or dipoles are aligned with one another, that means SI times SJ is +1. Their interaction energy will be minus J. So that interaction energy is minus J, it's negative, they prefer that, and its size is J. If the two dipoles are opposite one another, then the product of SI, SJ is going to, it's either going to be +1 times -1 or -1 times +1. So it's going to be a -1. That's going to make the interaction energy plus J, and so that's disfavored because of higher energy. Again, with this size or strength, J in units of kT. And so that's my whole scheme here. And this funny symbol here on the summation, this is just meaning I'm summing the nearest neighbors, just summing the 4 nearest neighbors. Yeah.
So that's like a really, I'm just wondering, so do large magnetic fields sort of like dampen this, the heat effect, or does it make it easier for them to flow? And like, because J equals 1 kilotesla is really large.
Yeah, so in this model here, I'm imagining there's no external field. So I don't know if that was part of, it sounded like that was part of your question.
More like the magnetic moment of the dipoles. So I don't know. I guess I don't understand what J is.
J is just so maybe what J is will become clearer when I implement the Boltzmann factor.
Okay.
But J is so if I make J bigger, that's saying that there's a larger interaction energy between the two dipoles.
Okay.
If I make J smaller, there's a smaller interaction energy. If I make J 0, there's no interaction energy between the dipoles.
Right.
Now, if we know that if I make J bigger, make a larger interaction energy between the dipoles, then they're more likely to overcome the thermal random process and line up with one another. If I make J smaller, then they're less likely to overcome this thermal tendency to randomize, and they won't line up with one another. So J is a number we can adjust in the code to make them interact strongly, make them interact weakly, to overcome more easily the thermalization effect, or the randomizing effect, or so forth. So that's the plan here. This, by the way, I now see where you're. This is not kilotesla.
That's what I thought that
Yeah,
was.
this is J of 1 means J equals 1 Boltzmann constant times temperature.
Oh.
KT is a
One
energy.
beta.
Yeah.
One beta.
KT is 1 beta.
Yeah.
Yeah, that would have been a better way, right?
Okay.
Okay. So that's the interaction. We specify that there. As I say, I'm going to start with some random orientation of the magnetic dipoles of my lattice. I'm then going to choose in step 2 here to flip one of them. So I'll pick like a coordinate on the chessboard, an IJ coordinate on the chessboard. If it's up, I'm going to try it and switch it down. If it's down, I'm going to try and switch it up. What's going to make me accept or decline that attempt to change its state is the Boltzmann factor. You know, if the energy of the new state is lower than the energy of the current state, then I'll just accept it 100%. I'll accept it all the time. If the energy of the new state is higher than the current energy of the current state, then I'll like only accept it with some probability that's going to be less than one. That is, I'll use this inhibition from the Boltzmann factor that it favors lower energy states over higher energy states to give some chance of declining and not accepting that change. And then we did this many times. Okay, let's go to the code. Where is it? Okay, so here's my code. Let me just start it running. Some of it, the latter parts of this code take a while to run. That's why I started running it then. But let's try and walk through the code. Let me make this a bit bigger. So this time when I wrote my code, I actually defined some user functions because when I show you the calculation of the magnetization of the magnetic energy, and I want to show you the calculation of the magnetic energy and the magnetization as a function of temperature. If I didn't use these user functions, it seemed to be complicated to kind of read. I wanted to take out the user functions as separate functions that we could just define, and then we could just use them in the code to simplify things. I think it also makes it easier if, you might want to change how you calculate the magnetic energy. Might want to not just use the nearest neighbors, might want to change that. And so you might want to have different user functions that calculate the magnetic energy in different ways. So I this time, unlike the last time, I did define some user functions. So I just want to go through those. They're just in the first cell here. One of them is a straightforward one. This is just to define the initial state. So remember I'm going to define I'm going to think about an array, two-dimensional array of atoms, molecules, or dipoles. And I wanted to just define the state of that array. And the state of that array will just be an array of plus ones or minus ones, depending on whether the dipoles are up or down along some axis or opposite some axis. So to initialize the state, the starting microstate of the dipoles, I'm going to later call this function initial state. The argument here is the size of each dimension of the two-dimensional array. So it's a two-dimensional array, n by n arrays. So I'm just passing the size of the array. I'm going to work to keep the program running pretty quickly, like a 10 by 10 array. So just 100 dipoles. I think in the homework, I make it a bit larger, maybe 20 by 20. 20 by 20 is fine. It's just I'll be standing here, not doing anything for an uncomfortable amount of time. So I made it 10 by 10. So we call this, and this function just contains this one core to random integer. Random integer generates a random integer. That's how we've used it before. Or it can generate an array of random integers, which could be a one-dimensional array or a multi-dimensional array. So here I'm asking it to generate a n by n array of integers, where the integer values are from 0 to 1 less than this value here. So actually, I'm generating an array of integers, two-dimensional, say 10 by 10 array of zeros or ones. Now I don't want an array of zeros and ones because I want ups and downs. So I want an array of plus ones and minus ones. And so we did this before. We just multiply this by 2 and subtract 1, and I got an array of plus ones and minus ones. So that we're going to use that. The next bit of code is to calculate this is a key bit of code. In the case of the internal energy of the gas, we applied a Boltzmann factor. So we needed to know the energy at the current state and the future state. In this case too, we're going to apply a Boltzmann factor. We need to know the energy of the current state, magnetic energy, the current state, and the current and the future magnetic energy. So we needed a code that will calculate the energy, which is a code that uses the interaction with the nearest neighbors to calculate the energy. So that's this chunk of code here. So I call this function calculate energy with these arguments here. J, remember, J is just a number in joules that characterizes the magnetic energy, interaction energy between neighbors. Configure is also a n by n or a 10 by 10 array that's the current microstate, right? We start with a certain microstate that was completely random. That's going to evolve. So each time I call calculate energy, I'm going to pass the current microstate, and that's what I call configure for configuration. So those are the arguments that I pass, and then it's going to return the energy of the entire macroscopic system. So I'm returning energy here. How does it do that? Well, first it initializes the energy of the system to be 0. This is just to find out the dimensions of the array. So as I say, in my example, I'm going to pass a 10 by 10 array, but it's going to look at config to inspect that to figure out the number of rows and the number of columns of the array. So it gets the number of rows and columns of my particular two-dimensional magnet. And then it's got a nested loop over the elements of that two-dimensional array. So again, just imagine a chessboard, right? Figures out the width in squares of the chessboard and the length in squares of the chessboard, and then it's going to have a nested loop to walk through every one of those squares on the chessboard. That's what the nested for loop is here. Okay, so I and J are going to be the indices of every magnetic moment in our array of magnetic moments. Now we're inside the loop. I'm looking at a particular coordinate in my two-dimensional array. So a particular square in the chessboard, and I'm setting S to be just the state of that particular dipole moment, that particular atom or molecule. So S is going to be a +1 or a -1, depending on whether it's up or down. So that's straightforward. Here I'm calculating kind of the combined state of all of the 4 neighbors to it. So it's got a neighbor to the left and right, to the front and back. Or in this language of I and J, it's got a neighbor at I +1, I -1, J +1, J -1. So if you look at all these indexes on configuration, which contains the entire state, there's I +1, J, there's J +1, I, there's I -1 J, and there's J -1 I. So those are the 4 referring to the 4 nearest neighbors. And so I am adding up the states of those 4 to see whether they're, maybe they're all pointing up, in which I'll get +4. Or maybe they're all pointing down and I'll get -4, or somewhere in between, right? Because it's really, I was saying that that ijth magnetic dipole interacts with its 4 neighbors, but we can think of it as a superposition of those 4 interactions. So I'm just adding up the 4 orientations. there's one little subtlety that you might see in here. This guy here. So, and what happens? What would happen if I had I was thinking of an IJ magnetic dipole that's right on the edge of the chessboard, right? I would try and look beyond the array of the chessboard. I can't look beyond the array of the chessboard. So I take the remainder of the division by the size of the chessboard. What does that do? If you're on the right hand end of the chessboard, it wraps you round to the left hand end of the chessboard. So some way or another, right? If I'm saying that I'm going to interact with the nearest neighbors, I have to do something special on the edges of the chessboard or on the edge of the array. There's various ways to handle the edges of the chessboard or the array. One way of doing it, which is what I've done here, basically imagines that the right-hand edge of the chessboard kind of wraps round to the left-hand edge of the chessboard, and the top of the chessboard wraps down to the bottom of the chessboard. And so this is one way of doing that. Okay.
Is it just periodic boundary?
Sorry.
Is it just periodic boundary?
Yeah, it's a periodic boundary condition. Exactly. You just imagine that really. Well, I'm calculating the 10 by 10 array, but that 10 by 10 array just gets copied and copied and copied off in all directions. So it's really kind of like it was an infinite array. And this is one way of handling that. Obviously, you could also, with a little bit more complicated code, you could say, well, if I'm on the edge, well, I've only got 3 nearest neighbors. Or if I'm in the corner, I've only got 2 nearest neighbors. So you can program that too, but it's and it just was the simplest one to start with. So anyway, so I add up the configurations of the 4 nearest neighbors. That means that this variable neighbors times this variable s is that sum. Remember, we had the sum over the nearest neighbors of Si, Sj. This is that sum over the nearest neighbors Si, Sj. That is that sum. And then I'm just multiplying it by the interaction strength and incorporating the negative sign for my ferromagnet. So this is now the energy. I increment the energy and I return the energy. The only other little subtlety here is, well, that nested loop actually double counted every interaction. Because I stood on one spot and counted its interaction with the neighbors, but I also stood on the neighboring spots and counted their interaction with it. And so that's the reason I divide by 2 here. Just one way of handling that. Okay, so that will calculate the interaction energy for us. One other simple function in here. What about when I actually want the magnetization of the solid? What is the magnetization of the 2D array? Magnetization of the 2D array is just the sum of the states of the individual dipoles, individual magnetic dipoles. So configuration, we can use this holds the state of the microstate of the system. If I add all the elements of configuration up, it's adding all the spin up ones with +1s, or the spin down ones with -1s. The net number is the overall magnetization. Now, if I've got 100 elements in the array and they're all up, the magnetization is +100. If I've got 100 elements in the array and they're all down, the magnetization is -100. If I'm somewhere in between, I'll get a magnetization that's between +100 and -100. So that's the calculation of the magnetization. So out of this, I've got 3 functions: calculate magnetization, calculate energy, and I got that simple function that just initialized randomly the initial state. Okay. This cell, I just wanted to use this cell to generate the initial state. So really, the only thing in this cell is I set up a couple of parameters that I need. This is going to be the interaction energy in units of kT. So it's a bit like half a kT. Whatever the temperature is, half kT, and this is going to be the size of my array. So it's going to be a 10 by 10 array. Then I'm going to call initialize state. And so configure is going to become the starting random array of the dipole moments. Don't need to go through this, but I'm just going to make a couple of plots to show you this initial state. So, and I'll use his plots later on also. So this plot here is literally the 10 by 10 array, where I think yellow is, say, +1, spin up and magnetization up, and blue is spin down, magnetization down. And so this is just the randomly generated array of spin ups and spin downs. This is just like we enumerated coin tosses or enumerated dice rolls. This is me enumerating how many spin ups and spin downs there are. So the blue is the number of spin downs, and the green is the number of spin ups. Now, it's like 100 coin tosses that we talked about in the last class. 100 coin tosses is unlikely to get 100 heads or 100 tails. We're most likely around 50-50. We see here, we're very close to 50-50. Maybe I got 52 ups and 48 downs from my random generation of this initial state. Okay, so that's just a look at the initial state. I printed out a couple of numbers because I calculated the energy and the magnetization of this initial state. So the magnetization will reflect the net difference between the ups and downs. So it could be as big as 100 or -100 if they were all aligned up or all aligned down. It's 2. It's just reflecting that statistically, you know, there's no net preference for up or down. So it's a very, very small magnetization on the scale of if I magnetize the whole array, and also the energy likewise. So it counts the energy of all the interactions. It could be a very large number with an array of 100 dipoles, and then all interacting with their neighbors. But it's really, so it could be hundreds, but it's really quite a small number because it's just they're randomly oriented. So that magnetic energy and that magnetization within fluctuations is 0 magnetization and 0 magnetic energy. Okay. So now here's a code. Yeah, I think I'm showing you all the important bit of the code where we're going to take the random walk, Markov chain random walk through the microstates. We're going to take many steps on our random walk through the microstate to burn in the system from this initial random orientation to the most probable microstates in the system, given that our dipoles are magnetically interacting with one another. We had a magnetic interaction energy of 0.5 kT, so a significant preference for the dipoles to line up. We want to see how that impacts the array. Okay. This list EI that I'm creating here, initializing here, that's just going to store the energy as I take this random walk of many steps through the microstate. So this is just going to be like an energy trajectory, and I just put in the first energy based on my initial state of randomly orientated dipoles. There's going to be also another list that I'm going to create of the magnetic energies sorry, the magnetizations of the dipoles as I take my random walk. So again, it's going to kind of be a magnetization trajectory on the random walk. Again, I can put in the first value for the magnetization based on my initial state. So this is a place where I'm calling calc energy and calc magnetic field to record the starting point. I'm going to define how many steps I'm going to take here. I'm taking 10,000 steps on my random walk. And then I'm going to have a loop where I'm going to take those steps. So now I've got into the for loop here, and with my index k, that is the label for every step. Once I'm in the for loop, I'm going to pick a random dipole to flip its magnetization from up to down or down to up. So look here, I'm picking I'm using random int twice to select a random I and a random j to locate some dipole on the chessboard. And that's the one I'm going to try and flip up if it was down, or flip down if it was up. So I've got my I and j now. I record the current energy of the arrangement. So just calculate the energy of the arrangement currently before I make the flip of this particular dipole in the array of dipoles. I then flip that dipole. So to flip the dipole, I just go to that one element of the configuration array that tells me how all the dipoles are pointing. And I'm going to change, if it was +1, I'm going to make it -1. If it was -1, I'm going to make it +1. So I just need to multiply by -1 to flip the dipole. So I flip the dipole here, and then I recalculate the energy. I calculate the new energy based on this slightly modified configuration here. So now I'm coming out of this with the new state and with the energy of the old state and the new state. Most importantly, the energy difference between the two states. So E minus E naught will be the energy difference. So it could have increased the energy, it could have decreased the energy. And this is where, statistical mechanics enters in the calculation, where we choose to accept or decline this change in the state based on the Boltzmann factor, and the Boltzmann factor's preference for lower energy states over higher energy states. So I generate a random number. So this is a random number from 0 to 1. If that's larger than this Boltzmann factor here, I'm going to reject the change. I'm not going to do the change. If that random number from 0 to 1 is larger than this factor here, I'm going to undo the change in the configuration. So I'm going to multiply that element of the matrix by -1 again. So it puts it back where it was. And I'm going to undo the change in the energy. I'm going to set the new energy back to be the old energy. So think about how this is going to work here, this statement here. Supposing the energy of the new state is less than the energy of the current state. So that means that E is smaller than E naught. If E is smaller than E naught, then E minus E naught is a negative quantity. That means that this exponent here is a positive quantity, which means that a random number from 0 to 1 will never be bigger than this E to the positive number, right? So you would never fail if the energy of the new state is lower than the energy of the old state. You'll never fail. And so we never undo it. We always accept it. However, if the energy of the new state is larger than the energy of the old state, then energy of new state is larger. So this quantity in parentheses is positive. That means that this quantity in the exponent is negative. That means that this exponential is going to be less than 1. If this is less than 1 and you're generating a random number from 0 to 1, then there is a chance that you will this will be true, and you will decline the change. So this implements the Boltzmann factor, this kind of weighting where if you go up in energy, you might decline, you might accept depending as a probabilistically depending on the energy change. But if you go down, you're always going to accept. This is where the Boltzmann factor comes in. Okay. So after either accepting or declining here, I've already got the energy of this state. Either it's the energy of the new state, or if I decline the change, it's the energy of the old state. I do also want to store the magnetization of the new state, whether it is actually a new state or it is just the old state because of the decline. So I calculate M, and then I append the new state's energy and the new state's magnetization to these trajectories in the energies of the magnetizations. And then we just go round and round and round again, taking this random walk. So I should say really that a couple of points about this. Every time I'm calling it a random walk, in a way it's a biased random walk because I don't always accept an upward shift in energy. So it's not truly a random walk. We're randomly selecting the atoms. We're randomly selecting a transition. But then I've got a rule about accepting or declining. So it's a biased random walk. That was one point. Also, there's when we make these energy changes, we are making, of course, energy is conserved, right? So I'm making a change in a state which increases the energy of the system or decreases the energy of the system. I think we're imagining that this system is immersed in some bath. Energy can flow in or flow out, ensuring that we conserve energy if our sample is in this surrounding bath. And so that's kind of how I imagine this. When the system equilibrates. So in the case of the gas, when we did the calculation of the internal energy for the gas at a given temperature, we started in the ground state, and typically then the energy increased and we thermalized. Well, it must have been that energy was obviously flowing in to increase the internal energy to match the temperature there. So embedded in our calculation is really the idea that when you thermalize, you must be in contact with some surrounding bath so that energy can be transferred or in or out. Okay. Well, we've gone around that loop. We've done our calculation. Let's see what we get. I'm going to just the rest of this cell is just some plotting. Let me show you the results. So I make the two plots that I did on the initial state. I've made them again now. So this is the plot of the magnetic moments of the 10 by 10 array. And this is the plot of how many moments are spin up and how many moments are spin down. So yellow is obviously now, I can see it. They spin up and blue is spin down. Maybe not expected, right? But not unexpected. We got a significant magnetic interaction. Because of that magnetic interaction, it wants to line everybody up. we've got a highly aligned state of the magnets in a two-dimensional magnet. Not 100% aligned. I mean, the preference for lining up is not overwhelming compared to KT. But it's substantial compared to KT, and so the atoms tended to line up with one another. And so that's what we see here. And quantitatively, we can see it in that now, I don't know, we've got, say, 96 spin-ups. Yeah, so 96 spin-ups and 4 spin-downs. So that's the effect of the magnetic interaction with the neighbors. That's one plot I wanted to show you. Another one is down here. We collected those trajectories of the energy of the system, magnetic energy of the system, and the magnetization of the system as a function of time. And that's what I'm plotting here. So the left-hand graph is the magnetic energy of a two-dimensional array of 100 dipoles. And the right-hand plot is the magnetization of that array. And the horizontal axes are the steps, these 10,000 steps that we took through the microstates. Look at the energy. We started with a random sort of collection of dipoles, and so very little magnetic energy. But because of the magnetic energy, they wanted to line up with one another, and you see them here starting to more and more to line up with one another as we walk through the microstate until we get to this point over here where they're mostly all lined up and we get a large magnetization. You see that, well, you see it here in the sorry, this was the magnetic energy. Here you see it in the magnetization. You see again, you start out with a small magnetization, they tend to line up because their preference to line up until we get almost fully magnetized. This case here. If I was to go back, see, let's go run back up here. Let's change this to 0.1. So I've changed that J value to 0.1. Now the magnetic interaction energy is 5 times smaller. It was 0.5. So it's now, you know, just 10% of thermal energy. What happens then? So I'll rerun the code. Let's see. Yeah, I think I can rerun the code starting from here. So this is my random starting state. I generated that again. This is just the fact that I got roughly equal numbers of heads and tails or ups and downs. I can then rerun the calculation with my 5 times weaker magnetic interaction between neighbors. We look down here. We've got now the situation in which the number of ups and downs is, you know, more equal. It's not as equal as just a random collection of magnetic dipoles up and down. There's definitely a preference for spin 1 state and spin over spin -1 state or down state. But that magnetic interaction energy is not fully aligned with material. And so we see the sort of development of magnetization occurring here, but it's certainly not fully magnetized. It's just partially magnetized. If I was to go back up here again, let's change this to 2. So first calculation, so it's now 4 times larger magnetic interaction with the nearest neighbors. Again, I randomly generate a starting point. This is just random ups and downs. This is random numbers of total ups and total downs, presumably consistent with statistics. Now let's run the calculation. And actually, I wasn't expecting this. So this one's interesting. It's like there's two good, but it illustrates an important. So we said with real ferromagnetics, you get domains of ferromagnetic material. So you get regions where, you know, macroscopically small, microscopically large regions where the dipoles are aligned, and then neighboring regions when they're anti-aligned. That's what happened here. We got a region, this region here where they're all ups, and this region here where they're all downs. We ended up with exactly 50-50. I don't know how that happened. Let's run that one more time, just see if, you know, if we get the same. I think I'm not setting the seed, so I think we should get a different case randomly this time. This is what I was expecting the first time. Normally when I've done that, I've seen that, you know, if you put in 2.0, the magnetic energy is now stronger than that 0.5, you get it fully magnetized. Here it's fully magnetized. There is one more code that I put in below. This one here. That'll take a bit of time to run, but I think this is along the lines of the homework. I showed you the examples of setting J to be 0.1, so kind of a weak magnetization compared to the thermal energy, 0.5, so similar to the thermal energy, and then 2, larger than the thermal energy. You could obviously, by using a additional for loop, making a nested for loop over J, changing J to scan the magnetization, the magnetic energy as a function of the interaction energy. And that's what I had done on this plot here. This works better if you do a larger array, you do more steps. And so I didn't have time to run that here, but now my horizontal axis is the dipole strength. And so what you're seeing here is that as you increase the magnetic dipole strength, the interaction energy strength, right? You go from sort of a low magnetization of the material here to a much larger magnetization of the material over here. Likewise, you go from a low magnetic energy to, because they tend to line up, a large magnetic energy over here when the dipole strength is larger. And so you can, with this model, explore the Curie temp, this critical temperature, where the onset of magnetization occurs. You can explore the development of domains. We saw one case where we saw different domains. And so with this rather simple Monte Carlo and this rather simple procedure, you can explore a lot of complex physics that is not, for sure, not in 2 dimensions, 3 dimensions, not amenable to analytical calculation. So that's really one of the paths of Markov chain Monte Carlo method for this icing model or other models. Anyway, I'm going to finish there. I've used up all my time. If you've got any questions, let me know. The homework is basically doing your own Markov chain Monte Carlo icing model for some dimensional array of dipole moments. Thank you.
Yeah, I have a question about the Curie temperature,
Yes.
because I understand that is the temperature that the magnetization starts to form. But then we are tuning the interaction energy J in the KT units. So let's say we have a larger J that that just means for example, for larger J, if we have a stronger or larger total magnetization, how would that correspond? Like, how would we determine the Curie
Oh,
temperature?
how would you determine the Curie? Yeah, the way so if the thing is, I think that question is backwards to how you would think about it as an experiment, right?
Okay.
So if you were given a piece of iron,
Mhm.
right, you could go out and you could measure the Curie temperature. Yeah, so maybe it's 1,000 degrees, right? And from the 1,000 degrees knowledge, you could then say, well, the interaction energy between the neighbors is
Roughly K times that.
yeah, it's what, well, you could say it's K times that temperature. What you're gonna find out here is does the magnetization become, is it when J is 1? Or is it when J is a half? Or is it when, so, and you'll actually be able to explore how sharp is the Curie temperature.
Mhm.
Um,
Yeah, so I guess it would be a range, right? Like,
yeah.
from certain T or correspondingly J
Mhm.
to another T or correspondingly
Yeah,
J.
yeah.
Between that, it's starting to drop the
Yeah,
magnetization.
That's exactly, because we say critical temperature or Curie temperature, but it's really not a temperature.
So-
And one of the interesting things about it is that it gets sharper and sharper as a transition when you go to 3 dimensions, for
Oh,
example.
okay.
Yeah. So 1 dimension is not a very sharp transition. Two
Yeah.
dimensions, it's getting sharper, and I think this is 2 dimensions, is it? So you'll see it there. 3 dimensions is getting, like with iron, it's really sharp in a 3-dimensional sample.
Okay.
Yeah.
So I think for our homework, we can just give a range, maybe.
Yeah. It's not meant to be precise or
Okay.
quantitative. Yeah.
Um, so, let's, so, so I'm just worried about getting the permission right here, whether or not, it's the same problem as having with the last thing.
Mhm.
So I'm making my evolve function that returns a list of energies and a list of magnetizations based on the number of steps. So, I have config as my microstate. So I added, if it's 1, I subtract 2. If it's,
Yeah, that looks fine.
and so this would be
Yeah,
my
yeah.
change in energy.
Based on the, yeah, I think that's right, yeah.
Because you're going from
Yeah.
S will
Yeah,
go from -1.
you did it a different way from me, which is good.
Okay.
You did it your own way, because I don't know the best way of doing it.
Okay, well, okay, cool.
Yeah.
So then I'm having it print out this DE. Because I'm getting a weird, here, I'll print out the Boltzmann factor. For each case. I get 0 for everything. But when I print DE. Let me cover this up. It's not like it's 1. Which I think,
Yes.
this is my J is 1/2. So,
Where is your Boltzmann factor test? Where's the truthful? Oh, here's the Boltzmann.
I'm just getting crazy values for my Boltzmann factor. I guess my KT. Is this? No, that's the constant. It doesn't specify a temperature. Should I do it in terms of J?
So you're defining KT based on a temperature, but your J is not in the units of KT.
Right. So I figured these 3 lines are from Tuesday. So I'm wondering how might we define the Boltzmann define this Boltzmann factor instead of KT in terms of like.
It's just defined in terms of J.
Yeah, I guess I missed that. Is it?
Yeah.
Do you remember what that is?
Well, is that, I just use calculate energy to do it. If you.
Yeah, I have that, I have an energy function, I have energy.
Yeah. But the point is, if it goes down in energy, when you flip one, it goes down by two J. If you go up, it goes up by two J.
Yeah, that's what I have here. J is 1/2, so this is two J. These are all two J. These are all two J. I have 10 steps. So these are all two J.
Actually, then what I just said is not right. It doesn't necessarily go, because it depends on all your four neighbors. So.
The four neighbors, wait.
This is changing that. Yeah, calculating.
So,
Oh.
so it could go, it should be changing by more than.
It should be changing by more than two.
Yeah,
It should be
yeah.
changing by 4.
If all four around you are up and you go down, that's gonna be a change of
If you go,
8.
oh, so this isn't the best one.
Yeah.
Cause I need a bunch of different conditions.
I did it by recalculating the energy of the entire array, which is kind of wasteful.
Yeah, I mean, I have that too. Energy list and run, and I run it here. But I guess
But
I could run it earlier, I could call
but you
something.
don't, so this isn't right, that's the point.
Okay, so
That's,
D.
yeah,
Oh, it's the total energy, not the energy of the individual.
yeah.
I'm calling it.
Although you're just flipping one thing up to down and vice versa, it doesn't mean that the energy.
No, I need to calculate the whole energy over again. Okay. Got it. Thank you.
Yeah.
See you next week.